Hi friends, welcome to follow up. In this video, we are going to analyze problem 2615, sum of distances. Basically, in this video, we are going to use some strategies based on partial sum and binary search. So we are going to do the problem gradually to demonstrate the thought process and also give you a walkthrough. First, let's look at the problem statement. So here we are given a zero-indexed integer array called nums, and there exists an array called array of length, the same length as the nums list. So where array I is defined as the absolute index difference over all g, such that nums g and nums I are equal. So here the indices are not equal. Actually, we don't need to restrict that, because if I and j are the same, then this absolute difference will contribute to the sum by 0, right? Nothing changes. If there's no such j, in other words, the element is unique, then we just set array I to be 0. So we want to return this array. This is actually very simple, right? So basically, this problem, the main point is that the length can be as long as 10 to the power 5, and we need to pay attention to the time complexity. Otherwise, we have a time limited problem. So here, I'm going to use example 1 to do an analysis, because example 2 is very special. All the elements are unique. Therefore, the output should be all zeros. So now let's look at example 1. So in example 1, so we know that the element 1 appears at index say 0, 2, 3, and the element 3 appears at index 1, and the element 2 appears at index 4, I guess, right? Then the result will be something like this. So the length is 5, right? So here for say index 0, so it's corresponding to 1. So this is the corresponding index. So because this is smallest, we are going to use 0 minus 0, 2 minus 0, and 3 minus 0. We are going to have 5. And for this index 1, the element is 3, but 3 appears once, so we just remain this 0. And for index 2, we have another 1. So this corresponding to 2, because we have smaller ones than 2, and we have larger ones than 2. So then we want to have 2 minus 0 plus 3 minus 2, right? So we're going to get 3. In other words, among the index left to the index 2, so we are going to the absolute difference will be 2 minus those indices and the summation. And right to the index 2, we're going to use those index minus 2 and do summation, right? So this is for this index 2. For index 3, so we get another 1. So, but this is largest one, right? So we are going to use this 3, use 3 minus all the other indices. So you can use 3 minus 0, 3 minus 2, and 3 minus 3. So we are going to 3 minus 0 is 3, 3 minus 2 is 1. So 3 minus 3 is 0. So we're going to have 4. So we get 4 here. So for last index 4, the element is 2. 2 is unique. So we are going to remain this 0. So this will be the return, right? So basically, we should have some idea, right? So here, for example, we have index I0, I1, I2, then up to ik, right? See, ik plus 1. So up to I of the n, right? So if you have some index, let's say ik, right? We want to set the values. So basically, you want to use ik minus I0 plus ik minus I1, and then plus up to say ik minus I k minus 1, right? If you like. So, but you know, if you count the number of ik's, right, you can have a count of ik's. So basically, the count will have the ik's will be multiplied, right? Then you minus I0 up to say I k minus 1. So the atom in the bracket is nothing but partial sum. So this is the one part. See, part 1. So P1, let's see. Then another part is to the left, to the right. So we get P2. This is nothing but, because IK is smaller, so we get IK minus IK, and then IK plus 1 minus IK, right? And then you have IN minus IK. Then basically you have IK up to summation up to IN, then minus the corresponding number for IKs, right? Then this is nothing but the tail sum. Basically the full sum minus the this part. So this is where we can use partial sum. So but in order to get the index, for example, for the index 2, is here. The insertion point will be, if you use left, you can have 1, right? Insert left. If you insert right, you have 2. So you are going to find the index which is to the left is less than or equal to 2 or strictly less than 2. This does not make much difference. But for this check, we can use binary search. So also we can use some strategy called space, trade space for time. So basically I want to use small space and then we accelerate the algorithm. So this is basically the overall idea. And writing the code actually is rather straightforward in logically. However, you need to pay attention to the indices, right? So here I will first write one solution, which is correct, but will have time limited problem, and then we are going to invoke this partial sum. First, I'm going to get the length of this nums list. I change this to be A just for convenience of typing. And then we are going to have a dictionary collections default dict. So we are going to use a list to hold the indices. Then we are going to iterate. So for I and Y in enumerate A. So what we are going to do is D of Y. So we are going to append the current index. So because the index, the way we retrieve this indices, so the dy result will always be a sorted index list. So once this is done, so what we can do is we initialize a result. So it's the same as length n. Then we set the corresponding values. So this is basically the for loop. So basically for I in range n, right? So the corresponding list will be, I will call it aux of d a of I, right? Then basically if length aux is less than 2, which basically says that this element ai appears once, then our unique element. So we just continue because we have initialized this at 0. Otherwise, we're going to set the values. So basically, we want to have something like this. Bisect. First, I'm going to get the index. I'm going to use bisect left. So search for this index list, and for this one. So I want to find the index which is to the left. So basically it says that aux I will be, let's see, I use say G. It's less than idx if not idx, then I if G is less than idx. That's the interpretation of bisect left, right? So basically it tells us that there will be idx number of element is strictly less than I and to the left. Then what we want to do is we set this one, right? So because there are this number of elements, this is less than I, we are going to use those i's minus the element. So basically the summation aux up to idx, right? And then we're going to do the other parts. The other parts will, because the I will be smaller, so we're going to use sum of aux minus sum aux up to idx, and then we're going to minus the number of i's, that is length of aux minus idx, right? This is the remaining element, then multiplied by I. So this way we finish setting the results variable, and then we just need to return the results list. So this is the one way to do this. However, if you check that, logically it's correct. So if you check in number 1, and if you check this one, for sure it's correct because all the elements are unique. But if you submit, you will get time limit exceeded phenomenon. Let's wait for some time. So here, time limited is due to here. So we do a lot of submission computations. So here, let's improve that. So here, I'll call this one version v1. So we didn't use partial sum here, and the time limited. I'm going to copy this part. So now I want to improve that. So here we have this dy. So this dy is used to find the do the binary search, right? But then I can use another one. So d2 is collections default dict. So I also use a list, but I want to change this a little bit. So for this one, it's essentially the same as d, but this time I want to store dy as the partial sums of the corresponding dy in d. So I'm going to do this. If not dy. This is the first time we can do this. So I'm going to do this dy like this, and d2y, because d2, though we store the partial sums, is just the first element, so we're going to append. Otherwise, dy is still appended, and the d2y is going to append d2y -1, the last element, plus the current index, right? So this will be d2y will corresponding to the partial sums. Then when we do this, I'm going to use temp as d2ai, right? So parallel to aux, it's corresponding to the partial sums. So here nothing changes up to now, and then when we compute the result, we want to do some changes. First, if idx is 0, in other words, no element is strictly less than this one. So this actually is a very simple case. So we're going to do the result I will be nothing but the total sums, that is temp -1, right, minus the number of i's, so it's length of temp or length of aux, the same. And otherwise, idx will be greater than 0. In other words, idx -1 is reasonable. So the result will be, so we can directly write corresponding to this line, right? So idx times I, right, minus this sum. This sum is up to idx -1. So basically we are going to have temp idx -1. And then we plus the remaining one. This is sum. This is temp -1 minus temp idx -1. This is the remaining part. Then minus the number of count of i's. That is length temp minus idx. So this is the number of i's, right? Then we comment out this one. So this essentially is the same, but due to this pre-computation or use this partial sum, we improved the temp complexity. So let's try this version. Let's pause the second example. Let's test example 1 to make sure it's correct. Yeah, it passes the first example. Now let's look at the generic case. it passes the generic cases. So that's basically where we accelerate the code. So basically here, essentially you can try to use one dictionary, but here I used some very simple strategy. Use space, trade space for temp. So essentially, if you compare v1 and v2, the logic is identical, right? So I guess this is a very interesting problem. Basically, in this video, we use the strategy partial sum, and we also use the strategy binary search, and also we used the trading space for temp. So this is actually a very typical strategy. So if you do more problems, you may match more such situations. So with that said, I would suggest that you try to write the code following this logic. So writing the code actually is not that essential in some point. So once you can digest and grasp the logic in the finer details, that would be the best. So with that said, I guess that's about it. So thank you for watching.